Hello everyone and welcome to the 8th tutorial. Okay, so let's get started with today's session. So today we will focus on not solving actually, the creation of the discretized system of equations in for a steady diffusion equation in a unstructured mesh. Okay, so before that I would like to give you a brief overview on the different type of computational grids uh, that are generally used in CFD. Okay, so yeah, so sort of a classification of a computational grid. So depending on the okay, so based on the structure, we can define the grids into either a structured grid or an unstructured grid. Okay, so okay, so based on structure, we can classify into two different types. One is structured grids and also unstructured grids. Okay, so by structured grid, what do we mean? We mean that the grids are spaced in a sort of a logical manner, right? So the grid lines follow a regular and a logical indexing system. So these are the grids. For example, if we can just classify them very easily, say I is equal to 0, 1, 2 and 3, and j equal to 0, 1, 2, 3 and so on, right? So we can easily get the points, and we can store the indices of the points and the locations quite easily, because all of them follows a logical system of indexing, right? So we can write follows a logical indexing system. Okay, so these are generally very robust in computation, and because we do not need any extra computational effort to store, or computational or the storage effort that is needed to store the grid points. We can just in a for in a logical manner store all of the grid points altogether. But the limitation of it is that we will not be able to construct very complicated geometries, right? So for very what do we mean by complicated geometry? For example, if we want to simulate a flow over a car, or some sort of a blob body, arbitrarily shaped blob body, for example a star or something like that. So in these regions we cannot have an ordered, let me just draw it here. For example, if you want to say mm, if you want to say want to compute something like a car, or let me just draw properly the flow over a car. Okay, so you can just means you cannot simply just put in grids like that, right? Because here you will have some improper cells, like for example you will have something like this in this side. Okay, so these will create problems. So what generally people do is that people tend to use unstructured meshes nearby. So for example some arbitrary shape, right? It can be a triangular, pentagon, or whatever. So what does it mean? That it does not follow any conventional or a logical indexing system. That is, it's quite haphazard in that sense. Something like this. Okay. Anyway, this is actually a very smooth body, so it's quite hard to understand. But structured grids you understand, and for unstructured grids, what do we have? That the indexing system can be arbitrary. Okay. For example, in I am just talking about the interior of a cell, interior of a domain. So it can be having something like this, a cell arrangement like this, some arbitrary. It can be composed of a triangle, a quadrilateral, parallelogram, whatever, right? So there is no logical system behind numbering each of the grid lines, right? But if you see a structured mesh, you will see that they are organized in a very logical manner. For example, you can simply index the vertical grid lines and the horizontal grid lines very effortlessly, and you can store them also very effortlessly, right? But in this case you will have to define each of the points by its own xi and yi's, right? And if it is a 3D problem, and zi also, right? And each of the edges will have different things. But here you see, you can just, if you just know the delta x, you can just go on, say the grid spacings are I times delta x plus delta x by 2, like that, right? So each of the points will have something like this, and y will have something like j delta y plus delta y by 2, right? Like some logical system will be there, which you can follow in storing these indexes. Now the problem arises when we have very complex geometries where we cannot afford to have structured grids. In those cases we generally tend to go for unstructured meshes. Okay. Now based on grid spacing. So what is meant by grid spacing? It means that what is the space between the two grid points, right? So it can be uniform grids, that is each cell centers will have the same delta x no matter what. But we can also have non-uniform grids, right? So generally the wall we have very high gradients, right? So in fluid flow, if you know, if you are familiar with the basic fluid dynamics, if you for example, this is the wall and a fluid is flowing over it, so you will have a very high gradients of velocity near the wall, right? So this is nothing but the u. So the u will have very high gradients. By that I mean the du dy will be very high, and to capture these gradients you will need very small cell size near the wall. But at the top, if you see, the gradients are not that high, so you can afford to have larger grid spacing. Okay, so what it turns out to be that generally in a fluid flow problems we'll have grids which are very fine. The grids, yeah, I think there was an interruption in the connection. I'm really sorry. Yeah, the screen is visible, right? Okay, thanks. Okay, so yeah, so where was I? So say in fluid dynamics, general fluid dynamics cases which involves some solid boundaries or walls, we'll see that we'll have very fine meshes, very fine resolution, very close to the wall, and as we go far away from the wall, where the influence of the wall is no more, we'll have much more coarser resolution. Okay, so let me just show you an example. This will make your clear. So okay, yeah, so this is a good example. It has both type of meshes actually. This is a good example. So if you see here in this part of the domain, we will have some unstructured grid points here, right? Because if you see, there is no grid lines and there is no apparent grid lines that we can classify into. Yeah, so there is no apparent grid lines that follows a logical numbering system or indexing system, right? But if we see in this region we see that there are quite definitive grid lines in the x and both in the y direction. So we can just easily classify them into I is equal to 1 2 3 4 and j is equal to 1 2 3 4 like this. And when you see, so this is a flow where this is just a step, this is a wall, and if you see very close to the wall, the grid spacing is very fine, right? So this is very fine here. What does this comes from the fact that the fluid flow over a solid boundary will have very high gradients near the wall, and to capture those gradients accurately and properly, we will need very small cell size very close to the solid boundaries, right? So this is an example of non-uniform grids. For example, you can have grids that are progressively getting smaller and smaller and smaller. Okay. Okay, so based on structure and based on grid spacing, so we have defined classified the grids into four classifications. So between are constant, not may, varies, right? So near the wall, if you see, we have some fine meshes here, or fine resolution here, but also if you see that we have a fine resolution in this region as well. Why is this? This is also because in this region some shearing will take place, which will again create very high gradients. So to capture these gradients also will require very fine resolution in this region. Okay. Okay. Based on orthogonality. Okay, so there can be orthogonal and non-orthogonal. What does it mean? It means that if you have two computational grid points, that is two cells, and which share a face f, and there is a line joining the two cell centers, right? So C0 and C1. If the line joining the two cell centers is perpendicular to the face, so if the line joining the two cell centers is perpendicular to the face, then we classify it as an orthogonal mesh. Thanks. And also if you see, there can be some cells like this also, right, where the face is a little bit skewed. Now here, if we join the two cell centers C0 and C1, we will see that this angle is not 90 degrees, is not orthogonal to each other, right. So this kind of cells are called non-orthogonal cells, right. So these are not independent things, right. So a structured grid can have a uniformly spaced grid. A structured grid can be a non-uniformly spaced grid. A structured grid can be orthogonal. A structured grid can be also non-orthogonal. Similarly, same goes for the unstructured grid also, right. So a grid can be structured, uniform and orthogonal, structured, uniform, non-orthogonal, and all other combinations that you can think of, right. So till now we have only restricted our studies to uniformly spaced structured grids, right. So now we will turn our attention to unstructured grids. Why is it that we want to do that? Because finite volume gives us the opportunity to create non-uniform, unstructured, non-orthogonal meshes, which we can in turn use to compute fluid flow over very complex geometries. Okay. So let us start the actual part of the today's session. So we'll do okay. So what does our diffusion equation look like? Then we do all the manipulations, integrate over the control volume, then apply the Gauss divergence theorem. Then we are finally left with what? The summation over all of the faces. gamma f, then f times area, right? Okay. Okay, so let's now create a geometry to work on. C naught, this is the cell center 0, C1, and this is the face that we are interested in. Let's A and B. Okay, so here so this is the coordinate system that we are familiar with, the x direction and the y direction. And in this case, if you look carefully, uh, the distance between the, okay, let me just draw it in another way, it will be, okay. So the distance between the two cell centers is not aligned with the x direction, right? And also the vector, the area vector, the area normal vector is not aligned with the any of the directions. Okay, so we cannot just take one of the components as we have done. For example, in the Cartesian coordinates, the gradient of phi was given by dou phi dou x I cap plus dou phi dou y j cap times some area. Area was nothing but, for example, in this case a y sorry, so a x I cap, so a I cap, so we'll just take dou phi dou x a, right? But in this case we cannot do that because both the directions does not align with the x and the y direction, right? Now, so what can we do? So we define a different coordinate system based on the phase that is shared by the two cell centers. One will be the direction normal to the face, okay. So let's define this as delta psi, and we'll define this distance as delta eta, okay. So one thing to note is that these the line joining the two cell centers and the face is not perpendicular. It might look perpendicular. Okay, let me just draw it in a way so that it does not look perpendicular. Or I can just change the cell centers here. C naught and C1, okay. and this is the distance del psi and del eta. Now we see that these two things are not perpendicular, right? So what to do now? So now what term do we have? We have, so we'll only consider this phase right now. Okay, we will not bother about the other phases. These things will be generalized for all other phases as well. So we have what? We have gamma gradient of phi at phase is nothing but gamma at phase f times I cap dou phi dou x plus j cap dou phi dou y. Okay, but we cannot write like this, right? Because anyway, means how will we compute the dou phi dou x and dou phi dou y, right? And we do not have these directions aligned with the x direction, right? Because the x is in this direction, and the line joining the two cell centers is having some angle with the x axis, right? So we cannot use the dou phi dou x and dou phi dou y directly. So we'll have to do some manipulations. So let's do that. But what we can do is that we can these values we have, right? So delta eta and delta psi we have, and we can define something like dou phi dou psi and dou phi dou eta, right? For dou phi dou psi it will be nothing but if this is phi naught, it is phi 1, it will be nothing but phi 1 minus phi naught by delta psi, and this will be nothing but if we define somehow we define this as, will come later how to define that, and phi a we can just write it as phi b minus phi a by delta eta, right? Del eta. So we can work with these terms, right? Okay, so let's just break these down. So we will introduce something some terminologies to simplify this. So this differential operator we will write something like phi sub eta, that means dou phi dou eta. Okay, and similarly for dou phi dou psi we will have something like phi psi. Okay, now using the chain rule, what we can do, for example dou phi dou psi we can write it as dou phi dou x times dou x dou psi plus dou phi dou y by dou psi. This is nothing but phi sub x sub psi plus phi sub y x, sorry, this will be y sub eta. Okay, and similarly for dou phi dou eta we can write phi x eta plus phi y eta. Okay, now let's club these things. We'll do some manipulations. So we have two equations here which are phi psi equal to phi sub x sub psi plus phi y sub psi, and phi eta phi x eta plus phi y eta. Okay, now this is say 1, this is 2. What we'll do is that we'll multiply 1 with y eta and take the and subtract with this, right? So what do have we left with? We are left with phi. Please stop me anywhere if you are feeling difficult to follow. So we have phi y eta this term and this term will get cancelled, right? This is the manipulation that we have done, and we have minus okay. Now we can formulate an expression for dou phi dou x, which is nothing but I'm sorry, there will be another term. This is the other term. So okay. So we have an expression for the dou phi dou x in terms of the natural coordinates or the coordinates described for that particular phase in mind. Okay, and this term, the x psi y eta minus x eta y is called the Jacobian. Okay, so Jacobian, what it does is that it's just it's a mathematical tool to switch between two coordinate systems. Okay, so for example, if you have one type of coordinate system, for example a cylindrical coordinate system, and you want to convert this coordinate system, switch this coordinate system to a Cartesian one, you can use the Jacobian which is responsible for that, and do the thing that you want. Okay, so this is called a Jacobian. Now we can do the same thing for the dou phi dou y also, which is nothing but we will do, we will have to eliminate the dou phi dou x term, and for that we will have to multiply with equation 1 equation 1 we have to multiply with x eta minus equation 2 x psi. Okay, and we will be left with something like yeah, it looks okay. Now we can just switch these terms from left to right by multiplying -1 to the top and the bottom, which will give us x Okay, that is also the Jacobian, right? So this is also the Jacobian. So let's write it down all together. So dou phi dou x, we have computed it as phi times y eta minus phi eta times divided by Jacobian, and dou phi dou y Okay, now that we have done these kind of manipulations, and we have these values, right? So what are we finally left with? So we'll have gamma f times I cap dou x plus times the area vector. This is the area in the, let's write as y, ay, in the, okay, okay. So these are the areas which are projected. So this is the area, right? This is the area that we have for our problem. So there should be a projection in the x coordinate, in the x direction and the y direction as well, right? So what will be the projections here? So if we just, right, so this will be nothing but ax and ay, right? These are these are just the two components of the area vector between these shared between the two cells. Okay, we'll see how to compute all these things also. Okay, now that we have all these things, we can just we not everything, we have only these parts, right? So dou phi dou x times ax and dou phi dou y times ay, right? So it will be gamma f Now let's put back the expression for dou phi dou x and dou phi dou y here. What was dou phi dou x? Now we will do another manipulation. We'll take this term and this term together and club this term and this term together to get our dou phi dou eta and our dou phi dou psi. Okay, so what are we left with? It's gamma f times this plus this. We have okay, I'm sorry, this will be ax and ay, right? Okay, so taking the dou phi dou psi as common, dou phi dou psi common, we have y eta ax minus of x ay divided by the Jacobian plus dou psi dou eta will take ay minus okay. So everybody clear till this part? I hope so. Now that we have these things, let's write down the different potential terms that has come up. Okay, so here let's start with dou x dou psi, which is nothing but x sub psi coming from here. So what it will be? It will be nothing but the delta x between these 2 points, which is nothing but, say, let this point be x1 and y1, and let this be x0 and y0. Okay, it will be x1 minus x0 divided by x1 minus x0 divided by delta psi. Okay, so it will be x1 minus x0 divided by delta psi. Now dou y dou psi will be okay. What other term is left? Dou x dou eta, which is nothing but x eta. What will be x eta? It will be x a. So for this part, this point will have something like x a and y a, and this part will have coordinates x b and y b. Okay, and this is the delta eta distance between these 2 points. So we'll have x a minus x b divided by delta eta. So we'll have x a minus. Similarly, we have y a minus y b. Okay. So we have all these terms. Okay. Now we will define a coordinate system by defining the 2 unit normals. Okay, so this is one of the directions. Let's draw it here. Okay, so now we'll define a unit vector in this direction, which we will name it as E cap psi, and one other direction in the B. So it will be along the parallel. If you have a normal vector, for example, a surface normal, you can find the unit normal vector. Okay. Okay. So now that we have all these things, what else is required? Okay, yeah, we require AX and AY, right? So let's see what will be the A. Hello? 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 Okay, okay. So, weren't you able to hear anything before now? Okay, okay. Now it's fine. Okay, okay, okay. Yeah, thank you for pointing it out. Hello? Okay, okay. Just give me 1 second.
about now? Is it fine now? Volume is very high. Okay. What about now? Is it fine now? Okay. What about now? Is it fine now? Okay. Please let me know. I'll try to get a new earphone in the next session. Yeah. Okay. So here we have defined the area in the x direction and in the y direction. Okay. So don't confuse, because this is a vertical line and I'm giving a x subscript here. It means that the area normal vector is pointing is aligned with the x direction, and here the area normal vector is aligned with the y direction. Okay. So here what will be the ax? Ax will be nothing but this is what? This is b is xb and yb, and a is xa and ya. These are the coordinates of the points a and b. So xa will be y. Yeah. Yes, Anand. You are not audible clear. Can you repeat? Okay. I'll again reshare the screen again. Okay, you just let me know if it's visible. Yeah, please tell me. No. So here the naming convention is based on the direction where the area normal points to. Okay. So this area, the area normal is pointing, the area normal is aligned with the x direction. Okay. That is why it is ax, and here the area normal is pointing towards the y direction. Not pointing, but aligned with the y direction. That is why it's ay. Okay. So now you have the ax value will be nothing but yb minus ya, and similarly the ay will be nothing but xa minus xb. Okay, it is nothing but the distance, this distance, right, and nothing but this distance. Okay. So now that we have everything that we need, let's put down, let's take the original equation that we had derived and substitute all the values, and let's see what do we have. Just copy these things also. Okay, so we have all these terms here now. So let's multiply y eta times ax. What do we have? So y eta is nothing but ya minus yb, and ax is yb minus y. Okay, and here x eta ay, x eta ay, where is x eta? Yeah, x eta ay, it will be nothing but xa minus xb delta eta ay is nothing but xa minus xb. Okay, so this comes out to be what? This comes out to be minus of ya minus yb whole square by delta eta, and this is xa minus xb whole square by delta eta. Okay, now if we just add these two terms, just substitute, just look at the first term here. Just take the negative sign outside. And what about this term? Let's look at this term once. It will be x psi x1 minus x naught delta psi ay is xa minus xb, and anybody wants to say something? Oh, okay, if not, you may mute yourself. And y psi will be y1 minus y naught okay. think I have done some mistake here. Okay, Okay, just give me 5 minutes, okay? I'll be back. I'll go to the washroom and come back. Meanwhile, you can just look at the derivations before and let me know if you have any issues till now. Okay, just give me 5 minutes. Okay, let's get back. I hope everything is clear till this part. Okay, now we have to do some manipulations. Let's see what the Jacobian was. It's the Jacobian. Okay, yeah, so this was the Jacobian, right? Okay, now what is the x eta value? X eta, we have x1 minus x naught by del psi times y eta will be y a minus y a or y b, y a minus y b Alright, so we have this form. Now if you see, if you look, compare these two terms. For example, if you take the dot product of E cap psi times and okay, so these are the areas, and we can write it as an area vector like ax I cap plus ay j cap, right, which is nothing but ya minus yb I cap plus x a minus x b j cap. Okay, so if you take the dot product between the area vector and the E cap psi, what will you have? So I am talking about these two things. So this I cap will result in x1 minus x naught times ya minus yb times delta psi, and this times this will be xa minus xb times y1 minus y naught by delta psi. Okay, so if you see, this term and this term has a lot of things common except for this delta eta. Similarly, this term also, right, this will also be of the same of the these are also the same except for this delta eta term, right. Okay, I think I have made a mistake here. This is yb minus ya, and this will also be xp minus xa. Okay, so if we just take the negative sign inside, it will be x1 minus x naught times ya minus yb by delta psi times 1 by delta eta plus xb minus xa times y1 minus y naught by delta psi 1 by eta. Okay, and this gives us what? If we just take the 1 by delta eta outside, it will be nothing but the dot product of E cap psi times the area vector, right? So the Jacobian is something like this. We can write the Jacobian in this form. to be a issue here. Yeah, someone has any questions? Can you repeat? From the diagram, okay. So from the diagram, what it says is that this is the vector of E psi, and we have a vector of area. This area vector we have one. This is called the area phase vector, and if we take the dot product of these two vectors, then we will get the Jacobian back, right? So this is the thing. So this is just a mathematical manipulation that we have done, that x psi times, this is the Jacobian that we have derived long back here in this part. This we have termed something called a Jacobian, and we have the form of Jacobian here. So what we have done is that we just rewrote the equation in terms of the area vector and the natural coordinates E psi and E eta. Okay. So this is just a mathematical manipulation. No need to get too deep into it. It's just for convenience we do this kind of things. So finally, when we have this form of the Jacobian, we can just plug it inside and see what happens. Now again, I think it's getting a bit clustered. Let me go to the next page and do it again. Right, we had the Jacobian like this, and we had derived the differential terms dou x, dou psi and dou x, dou eta in terms of the coordinates we had, right? So if we just expand all these things, this will be nothing but okay. And what are the area vectors that we had defined? The other term is this one, right? this we had defined it as I cap x1 minus x naught plus j cap y1 minus y naught and divided by the magnitude of the distance, which is nothing but delta psi. Okay, till now it is clear, right? I hope it is clear to everyone. Now, if you do a dot product of these two terms, AF vector and E cap psi, the I cap terms will get multiplied with each other, which will give us a x1 minus x naught times yb minus ya divided by what? This is delta psi plus xa minus xb times y1 minus y naught by delta psi. Okay, now if we just compare these two things, okay, if we compare these two things, we can just take the negative side sign inside, and we'll get the Jacobian is nothing but the area vector times E cap psi divided by delta eta, right? I hope until now this is quite reasonable. Now that we have the Jacobian written in terms of the known quantities, and what are we left with is that at the top part we have y eta and y eta x eta times delta x. We can again do another manipulation. So let's do another manipulation here. Let me just take this thing down so that it's easier to understand. Okay, so now what we will do is that we will look at this term. So what does this term actually do? So y eta, what is y eta? We have the value for y eta, which is nothing but yb minus ya times delta eta. And what is the ax? Ax is yb minus ya, right? So yb minus ya. Similarly, minus of x eta, which is nothing but xa minus xb by delta eta times what is ay is xa minus xb again, so xa minus xb. Okay, so now that we have these things, we can clearly see that this is nothing but I think we have to do another manipulation here. So x eta was something, there was x eta, I think I have written it wrongly. Xa minus xb, right? Xa minus xb, and this is xb minus xa. Let me check where. And this will be xb minus xa. Then we will again take the negative sign inside, so it will be yb minus ya whole square by del eta plus xp minus xa whole square, or okay, this is xa minus xb by delta eta. Okay, and what does this term look like? This is nothing but the inner product of the area vector, right? So this will turn out to be af times dot af by delta eta. Okay, so this term we have computed, this term also we have it with us. So finally, if we just assemble all of them together, it will be gamma f dou phi dou psi, it will be af times af by delta eta. And what was the Jacobian? Jacobian was af times e cap psi by delta eta. So delta eta by af times e cap psi. This will get cancelled out, and this is the other term. Let me write it like this. So this term, what it becomes? It becomes gamma f and af dot af by times e times psi times dou phi by kilometer, right? And we can finally write it like this by delta eta okay. This is the first term only. Okay, now we will again have to see for the second term what how things play out. So till now any questions? So this is a lot of algebra. I think I have messed it up here and there, but I'll suggest you guys to do it by yourself. It's quite simple. You just have to be patient and do it till the end. Then you will get what we are having here. Now let's get back. So here the Jacobian we already know, right? We already have figured it out. We have a relation for that. Now we'll have a look at this term, x psi ay, y psi ax. So okay, so this will be nothing but xa minus xb divided by delta psi, this term, and our ay is nothing but x1 minus x0, right, plus, sorry, not plus, it will be minus, minus of y psi will be y1 minus y naught by delta psi what is ax? Ax is nothing but y b minus ya. Okay, so now that we have this, what we will do is that we'll do a slight manipulation. We'll take negative outside, xp minus xa times x1 minus x naught by delta psi. This will also be minus, right? Minus of yb minus ya times y1 minus y naught again by delta psi. Okay, and we can just take the negative sign outside. This will be something like this. Now we will compare it with another dot product and see how what comes up. Okay, so we have the two area normals, two unit normals. These are the E psi and E eta. Where are they? Yes, here we have it. x1 minus x naught, y1 minus y naught. So E cap psi is 1 minus x naught by and it was xp minus xa ya. Okay, so now that we have these two area normal vectors, the unit area normals, we can see that this thing, if we just take a dot product of these two things, E cap psi and E cap eta, what will we have? We will have something like x1 minus x naught times xb minus xa by and plus y1 minus y naught and yb minus ya by delta psi delta eta. Okay, this is nothing, this is just the same as what we have here, right? So what we need to do is that we can just replace this thing with, so what was this? This was the x psi ay, x psi, sorry, ay minus of y psi ax. Ax is nothing but negative E cap psi dot E cap eta times delta eta, right? Because we will have a we have the delta psi here and we have another accompanying term of delta eta coming from the dot product, so we just need to multiply it with delta eta and we'll recover the same equation that we had. Okay, so now that we have all these terms, so finally what will we have? We have, so the gamma f grad phi a vector is nothing but gamma f af dot af by af times E psi cap plus dou phi by dou psi plus xf. What was the Jacobian? Jacobian was AF times E cap psi times what was the Jacobian again? Let me check. Delta eta, and at the top what do we have? This is the AF dot AF by delta eta times AF dot E cap psi by delta eta times minus of E cap psi times E cap eta times dou phi dou eta at the face F. Okay, so now just cancelling all these terms, so finally we are left with gradient of phi times A vector is AF dot AF by so minus term will come from this side, right? So this will be minus gamma F AF dot AF for E cap psi times E eta E psi times E eta dou phi dou n at face F. Okay, now that we have this, so this term we'll call it as the primary and this will be the secondary gradient. Secondary gradient is a bit tricky to get, but again we'll see how to do that. And this term is quite simple, right? So dou phi dou psi will be nothing but dou phi 1 times phi naught by delta psi, right? You can just replace it here and you will get that. But what about the dou phi dou eta? So if you see, if you remember the diagram from before, C naught C1 was A and B. So to get a gradient here we'll need something like phi B phi A by delta eta, right? But we do not have the phi B and phi A, right? So how do we get all these things? So for example, if you have cells here C0 C1 and C2, C3 and C4. What we will do is that we will take a interpolation. We will just assume that assume it to be a interpolated value, and get the phi b here and phi a here, and then we will compute this. But this is a very tricky business, right? Because in a particular time step, if you are using a implicit solver where you do not have the values of the cell centers at the current time, you will have to take the values at the previous time, right? So what we do is that we take the star values or the previous time step values and compute the secondary gradient. So the secondary gradient does not come into the coefficient matrix. For example, if we have something like a phi equal to b, where a is the coefficient matrix and phi is the variable vector and b is the constants or the known values. So this secondary gradient will come into b. Okay, but you will again have to do extra iterations for this to converge, because there is a mismatch between the cell center values. The secondary gradients you are computing using the deferred or the previous time step values. So as a result, you will need to do multiple iterations. So so this gets a bit tricky, how to compute the secondary gradient, and it imposes a lot of computational effort when you are doing some sort of a implicit solve. Okay. So this part we can write it as, so phi f gamma phi a at particular phase is nothing but gamma phase. Let's write it as PG, or primary gradient, some primary gradient coefficients that we will compute, and finally by delta psi phi 1 minus phi naught plus the secondary gradient. Okay, which is a known value, because even if we are doing a implicit solve, we will take the previous time step values and we'll take it to the b vector. Okay, which imposes another constraint on convergence, which I think sir has covered very well. So this was the basic this was the basic introduction. There is a lot more to cover, but today I'll like to stop the session early, because I have a important work tomorrow, so I have to do some preparations. But I'm willing to take any questions, any doubts. This is quite a mathematically very intensive work to do. I'll recommend everyone to do it by yourself. It's just basic algebra, but it will be very good if you could do it yourself and derive it by your own. Okay, so any questions till now? Anybody, any doubt? Yes, Vibraj. Vibraj, your voice is breaking. It's coming very slowly. Can you just bring your microphone close to your mouth and speak, so that it's or you can just type it in the chat. I'll try to answer your question. Yeah, I think today the audio was really bad. I'll try to compensate it in the next class. Oh, okay, implicit. Okay. So for example, if you have a unsteady problem, right? So dou phi dou t equal to dou by dou x. This is the unsteady diffusion equation. Okay. So this part is then again you will do a integration and all that stuff. Then finally what you are left with is at t plus 1 minus phi at t by delta t times delta volume with some function of phi. Okay, this is point I, okay, or point P. So what you are doing is that so you are at some time t and you want to progress your values from time t to t plus delta t. Okay, so this temporal derivative discretization comes out to be something like this, which is nothing but a function of this. So this will be, I think, quite you guys are quite familiar with something a p phi p times a e phi e, something like that. All the things you know. So now the implicit part comes about, so you can just break it down and write it something like this. T plus 1 will be a function of, say, a p phi p plus summation of a n b phi n b, something like this, right? So you will have this kind of form, right? So now if we take the values of these, if you take the values of the cell centers phi p and the neighboring points at the same time step, that is the time step that you don't know, then what will you end up with is a system of linear equations, right? So you will have system. What does a system of linear equation means? It means that something like this: a x1 plus b x2 plus c x3 dot 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 d x1 plus e x2 plus f x3 dot 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 equal to some alpha 1 alpha 2, like this, right? So you will have multiple equations. So the number of cells that you will have, so if you have n number of cells, you will have n equations like that, and if you will have n equations and n variables, right? So you will have an equation for each of the cells with n variables, right? So what will you end up with? You will end up with something like an ax equal to b sort of system where you need to find x, right? And we saw that if the A is a banded or a tridiagonal matrix, we can use certain methods like the direct method, which is the Thomas algorithm, or the TDMA method, or else we can do an iterative method like Gauss-Seidel or Gauss-Seidel, and what was the other one? Jacobi's method, right? So yeah, so the concept is that, so when you are doing a temporally varying system or an unsteady problem, if you end up with a system of linear equation, that is, you are using the values of the neighboring cells and the cells at the current point of the same time step, that is, all of these are unknown, this will result in an implicit solve, right? But if you have something like this, for example, if you have phi p t plus 1 is only a function of phi I at the previous time step, right? So in the stability part of the course, you guys have seen the importance of the implicit and the explicit schemes. So yeah, so this is the main concept. So if you end up with an equation which has which is a system of linear equations, and you use the values of the cell centers at an unknown time step, then you end up with an implicit sort of a system. And when you use the cell values at the previous time step or a known time step, then you are just left with a algebraic equation, right? You can just straightforward solve this because all of these are known, but in this case these are not known, right? So this is something called explicit time stepping. Okay, so I will recommend you to go through the lectures once, or else you can go through the previous tutorial, I guess tutorial number 7. Yeah, there I have discussed in details, or else in the next class please formulate your question, like what specifically you want to understand, and if you just point to me, and then I'll again do a small demonstration of how to deal with an explicit and an implicit time stepping scheme. Okay, I hope it was a I was able to make you understand. So if there is no more questions, then I would like to end this session today. It's a bit early, but I have a exam tomorrow, so I have to prepare also. Okay then, thank you guys. I'll see you in the next tutorial, and hopefully in the next tutorial I'll have a good microphone, and I'll be able to explain to you the next part of the how to discretize the steady diffusion equation in an unstructured grid. Okay, thank you guys. I'll see you in the next tutorial.